Oh, yeah. But I will switch off my microphone. So
good morning, everybody. Thank you very much for organizers to invite me for this conference. And thank you very much all people which woke up so early to listen to this talk. I would like to tell you about the transition metal dichalcogenides. It is quite new materials in condensed matter physics. Then about neutral excitations in these materials, and finally, I would like to present some results of experiment performed by people presented here and from these different places, institutions and universities. So transition metal dichalcogenides are materials which with chemical compounds mx2 when M is transition metals and X it's chalcogens. 1 minute. Do you see my mouse? Yeah.
yes, we see.
Okay. Sorry. So and the materials, metals, and chalcogens in red frame, they form so-called semiconductors, semiconducting transition metal dichalcogenides, the object of our main interest. The bulk materials looks like this, so they looks gray, but they, as you see, they reflect a lot of light. So bulk materials do not absorb a lot of light. But these materials are layered materials, so they are formed from layered layers, which are two-dimensional crystals, which presented here. So two-dimensional transition metal dichalcogenides monolayers have a hexagonal structure, and they also also can be presented as a sandwich where metal atoms are encapsulated between two layers of chalcogens. These materials have plane mirror symmetry instead of typical inversion symmetry as many conventional semiconductors have. And finally, we have a hexagonal brilliant zone, and since this is hexagonal materials, but as we will see later, the most interesting physics appears in K and minus K points in the corners of these brilliant zones. So why monolayers are so interesting? So these materials in bulk form have been studied in 70s and 80s, and finally nothing interesting people saw, especially in the optical properties. This is because the bulk is so-called indirect semiconductor. It means that the top of a valence band and the bottom of the conduction bands are aligned in different points. So the valence band is in the gamma point in the center of brilliant zone, and the conduction band is in the Q point in the middle, somewhere in the middle of the brilliant zone. And there is a huge momentum between them. So that is why light cannot be absorbed by these materials, because light with the corresponding energy carry much smaller momentum. And as it was shown in 2011, this situation takes place for 4-layered materials and even for 2-layered materials. But situation is dramatically changed when we come to the monolayer. In monolayer, the band structure is significantly changed, and this material becomes a direct band gap semiconductor. The valence band and conduction band extrema are aligned exactly in the K point. In this case, the light can be absorbed quite easily by these materials. So if we zoom this rectangular, we will see more complex back structure. Even namely, we have two valence band and conduction band are spin split, and then spin splitting in valence band is around hundreds of millieV. In conduction band, it's around tens millieV, and the distance between bands are 1 or 2 electron volts. sign minus here means that the orientation of the spins is opposite, as it in such situations opposite as it presented here. We have two types of transitions which conserve spin. So we have a low energy transitions, which called A exciton transitions, and we have higher energy transitions, which called B exciton transition, B type transitions. But what is interesting in this material? So we have a semiconductor, two-dimensional semiconductor, which interacts strongly with light. So it can be used for nano or optoelectronics. That is why this material is important to study. Let's look on our materials in key points more carefully. So as I told before, so there are two types of transitions, lower energy and higher energy states. And these materials possess more additional properties. Namely, since they have a time reversal symmetry according to Kramer's theorem, the spin orientations of bands in opposite valleys should be opposite. It's called, this property called spin valley locking. Moreover, if we look on the optical polarization rules for transitions in these materials, we see that in minus k point or minus k valley, only circular polarized light with with negative helicity can be absorbed, while the sigma circularly polarized light with positive helicity can be absorbed in the k plus point. So it allows us to manipulate the optical transitions by photons. So if we have a photon with a given helicity or circular polarization with fixed energy, we can absorb, we can make this transition exactly in the minus k valley, for example, and we will know that it has the transition is between the bands with spin down states. This property is interesting because we have a triad, a spin, valley, and polarization, and then use one of them to manipulate by other degrees of freedom. So this property with circular polarized light can be observed easily from the Hamiltonian of the bands minus k and plus k valley. So this is 4×4 Hamiltonian. So each element should be considered as a 2×2 matrix. And if we want to include electromagnetic, so it describes the propagation of electrons in each bands. And if we want to include the magnetic field in this interaction with magnetic electromagnetic field in these materials, we need to do the following. We need to come to the coordinate space. So first we need to replace all k by the gradients or the components. When we need to elongate the gradient to adding by electromagnetic field A. And if we substitute, make this substitution, we will see that the off-diagonal terms get the additional linear in electromagnetic field terms, which couple conduction band states and valence band states. So, and this coupling of conduction band states and valence band states with electromagnetic field means that there is a term which causes the transitions. But this coupling is interesting because in minus k valley, it couples to the electromagnetic field A plus, so it means AX plus E AY, and in k plus k valley, it's coupled to the electromagnetic field with vector potential A minus, which means AX minus EAY. So on the on the level of Hamiltonian, we can see that indeed there are such optical rules. So, and again, so using the circular polarized light, we can manipulate the excitations, electronic excitations, exactly in minus k valley or exactly in k plus valley. The interesting part of this material is also that they possess another type of transitions which causes spin flip. So it means that it's second order, in leading order perturbation, this type of transitions are forbidden because typically or usually optical transitions conserve spin as it was before. So it couples the bands with the same spin. But in the second order, it's possible to find the terms which are responsible for these transitions. These transitions will be weak. And the origin of this transition is can be understood in the following way. So if we, as I told before, this material possesses the mirror symmetry, and all the electronic states can be classified by parity of according to this mirror symmetry. So, for example, valence band state and conduction band state has the same parity, but the next conduction band state of these materials has opposite parity, negative parity. And if we violate the mirror symmetry by putting this material on the electric substrate, by applying electric field perpendicular to the plate, or by shining the light to this material which has a non-zero Z component, we can induce these transitions. And these transitions can be described as a two-order process. So first, we by violation of the symmetry couple valence band and higher conduction band with different parities, and then using the spin orbit interaction term, which contains elements with a spin flip, we can come back to our conduction bands, but with flipping the spin. So in general, after this two-step process, we get the following transitions. I want to point out that there are no transitions, higher energy transitions of such type. So this is some sort of...
Excuse me, Artur, how would you introduce this out of plane electric polarization? I missed it. Do you apply electric field, or this is from the wave electric field is coming?
There are three ways to do it. You can apply electric field perpendicularly to the monolayer. So this is the easiest and the most clear way. Second, you can put it on the electric substrate. So from electromagnetic point of view, so since the electric constant of a substrate is doesn't coincide with the electric constant of air upper of the band, upper of the monolayer, it also can be one can calculate that it's also causes some sort of symmetry violation. And finally, the most interesting that photons which propagates in parallel or close to parallel to the monolayers plane also can induce this mirror symmetry breaking, and so it induced this breaking, and then absorb in this breaking caused the absorption of this photon. This is it looks like a second order process, but this is the first one. So finally, what I want to say that this mirror symmetry breaking opens us two possibilities. First, it's spin flip transitions described here, but it also tells us that the monolayer can be polarized electrically in the direction perpendicular to monolayer's plane. And this is quite surprising and quite interesting because no one can imagine that monolayer, so like a bunch of atoms with a free angstrom can be polarized. So, so this is very funny observation of these processes. So, but what happens with this with electrons after transition? So, when we have a transitions, we remove electron from valence band and put it to the conduction band. So, in physical space, it means that we create an electron and a hole on some distance from each other. Electron and hole has the opposite charges and can be and attract to each other by Coulomb interaction, and can form the bound states. These bound states are called excitons. And the standard description of excitons is the following. So this is a two-body problem. We can separate the movement of electron hole pair in two parts. First part is movement in the center of mass, system of center of mass, and inside this. And second one is moving of these two particles as a whole. So moving two particles as a whole, it's like moving of object with momentum q, some momentum q, and the inner motion inside can be described by solving the Schrödinger equation. Solving this Schrödinger equation with a reduced mass, which you can derive from the curvature of these bands, gives a spectrum, and we take the lowest energy spectrum of this equation, find the wave function, and we can organize this two objects. First, so these wave functions are here for bright exciton. This is RB, it's coordinate of center mass of electron hole pair. And for dark exciton, it's the same. So we have a wave function of dark exciton, which is not equal to bright one. And we have momentum of dark exciton with RD is the coordinate of center of mass of dark exciton. So, and this part describes how we create the electron hole pair. So we have a vacuum state, which corresponds to valence, full filled valence band and empty conduction band. We apply annihilation operator in corresponding valley, in K plus valley, for example, which acts on valence band state, and remove the electron with spin up. When we create an electron with spin up state in conduction band in the same valley. So we have electron hole pair with different coordinates, and we need to integrate these coordinates with this function and get the so-called bright exciton state, the state which appears due to circular polarized light. In the same way, we can create the dark exciton states. If we substitute these states to main Hamiltonian or Hamiltonian of these states, we get we observe that these states are mostly eigenvalues of the Hamiltonian with corresponding energies. So it's a constant energies which defines by position of the bands, and there is a q-dependent part, so which is just kinetic term of excitons with total mass m, big M. It's total mass of electron in the hole. So it propagates like a neutral particle with momentum q. However, as I told before, it's mainly mostly eigenstates, but the excitons, they are neutral, but they are characterized by the dipole moment. Therefore, there is interaction between them, which can be rewritten in terms of dipole-dipole interaction. And due to this dipole-dipole interaction, these excitons, when they are moving, we create a new type of, instead of 4 lower energy states, 2 bright states, and 2 dark states, which couple corresponding bands, we have another 4 states, which are called transversal and longitudinal excitons. So if we take into account the interaction terms, we can solve the corresponding. We can find the real energies of these excitons, because this part is only main part, but not the full one. So in order to find the new energies of these excitons, of new transversal and longitudinal excitons, we need to solve the following equation, which has the following meaning. So the excitons is a source of polarization, which is a 3-component vector. So all the Greek indices here are 3-component. If the polarization induces electric field, here, in order to write it, we need to apply multiply this polarization on the green function of photon reduced to monolayers plane. So this object is electric field in some point of a monolayer. This electric field polarizes the material again in 3 directions and create the polarization. And this answer should coincide with the polarization of a material. So this is a self-consistent equation which defines us the eigenstates or direction of polarization of real excitons, and gives us the shift of energies, which can be calculated in the following way. So we need to solve it. We need to find the eigenstates of this equation, and substitute them here and find which energy shift. It contains a real part. The real part will give us an energy shift, and the imaginary part gives us a radiative decay rate. So these excitons are no more stable. They can decay into photons as it should be. So, and this decay can be understood from this picture. So if we draw the bands, the energies of excitons as a function of the two-dimensional momentum, and draw in the same plot the dispersion law of photons, we see that we can satisfy both energy conservation and momentum conservation only at small region, which is called radiative region, of a small range of momenta. So it means that, of course, the interaction is important, and at large momentum, the energy shift is large. But in physical observable cases, so if we want to consider the decay of photons or of excitons, we can take this limit. So, and in this limit, the situation becomes simplifies, because we again come back to our picture of four type of excitons.
Excuse me, am I right that this small q can be regarded as a momentum of a photon, or this is wrong?
This q?
Too small.
Q is a momentum of exciton, but it's also the in-plane projection of the momentum of a photon, yes.
Oh, okay, thank you.
Yeah. So what I want to say, that at small momentum of excitons, or we can put this momentum equal to 0 for so we have just standing excitons which are not moving anywhere. We come back again to the system with the four excitonic states: too bright and too dark. And the emission of these excitons is the following. So this is a radiation pattern of bright excitons. So where transition dipole moment are in plane to the monolayer. So radiation is mainly perpendicular. The main part of the radiation is perpendicular to the plane, and this light can be easily absorbed by lenses in experimental setups. And transitions, dipole moments of dark excitons are perpendicular to the monolayers plane, and the radiation pattern has an opposite, it propagates in opposite direction. So the main part of the light, if we want to collect the light from dark exciton, we need to put lens here. But in experiment, it's quite hard. Therefore, instead, if we take a lens with a high aperture, so we can get some small amount of dark excitons, emission from dark excitons from this small corner. Okay, so this is excitons in these materials, and of course it's interesting to look what happens, what we can do with these excitons. As I told before, so that is why it's the easiest way to do it. It's to consider the effective Hamiltonian, which acts only, which couples only these four states. So we need to take, to do it, we need to take the main Hamiltonian, reduce our space of states only for few, for these four excitons, and calculate the matrix element and form the 4x4 matrix, which acts on exciton stance in the following way. So this is first line corresponds to bright exciton in K plus point. Second line corresponds to bright excitons in minus K valley. Third line corresponds to the dark exciton in K plus valley. And the last one corresponds to the exciton, dark exciton in the minus K valley. So the energy of excitons are different, so it's easier to calculate them from the energy of the dark one. So the energy of bright one is just larger than on the delta, on the splitting between the bands, which is here. As I told you before, so we put a Q equal to 0. And if we put Q equal to 0, we will see that indeed there is no additional interaction between bright excitons. So, but there is interaction between dark states, and this direction appears from this dipole-dipole, and it forms. So this is 2 by 2 matrix.
Sorry, please switch off microphones if you are not the speaker.
So we can see that bright at 0 momentum, the bright excitons do not interact with each other, but the dark one interact due to dipole-dipole nature. And instead of having 2 dark excitons in different valleys, this interaction couples them and form the 2 new types of excitons, so-called gray and dark and truly dark excitons. It means if we take these states and calculate their dipole moments, apply them and calculate their dipole moments, we will see that gray excitons, the ones which are plus here, they have a dipole moment, but these states, D excitons, dark excitons, with sign minus here, they do not have any dipole moment. But that's why only gray exciton with linear combination corresponds to the state which optically active. So instead of having 2 separate dark states in different valleys, we have 2 linear combinations which has and only one of them, only one combination is optically active. So what happens if we apply magnetic field to this material? If we apply magnetic field which is perpendicular to the monolayers plane, we shift the bands, and the shift of these bands is opposite in different valleys. And the shifting of bands cause the shrinking or extending the energy of excitons, so which is presented just by diagonal elements here. BZ here, BZ is a magnetic field written in energetic form, so it's real magnetic field multiplied by magneton Bohr's magneton and divided by 2. And magnetic field BZ can be used to manipulate by dark excitons. Indeed, so again, so we have this 2 by 2 matrix for dark excitons, and we know that we have 2 types of excitons which are linear superposition of the dark states. And but one can see that if we apply increased magnetic field, we can easily change the content, so amount of these numbers. So and we can change the superposition of the states, which corresponds to the superposition of dark excitons. So what happens if we apply in-plane magnetic field to the monolayer, our monolayer? So monolayer couples the states, magnetic field couples the states with opposite spins and mix them. So this is in single particle electron picture, but in an exciton picture, this mixing, so this coupling of the states with opposite spins means that the bright state and the dark state in corresponding valleys are mixing. So instead, if we apply in-plane magnetic field, instead of having dark state in K plus point, for example, we will have this dark state plus some other mixture of bright exciton. It means that if we apply magnetic field, so the dark exciton, when you with corresponding energy, start to emit also light not only in Z direction, in plane direction, but also small. They can emit the light in perpendicular direction. Again, so if we remember, so we don't have now valley dark states, so the states which corresponds to each valley, we have their superposition. So if we put this substitution to our superposition here,
Artur, you have 10 minutes left.
Okay, we will see that the gray and dark excitons start to emit linearly polarized light in direction perpendicular to the monolayer, and they will be, their polarizations will be orthogonal, which appears from the orthogonality of these states. So finally, if I apply all magnetic fields in Z and in plane and out of plane directions, we can easily manipulate by light which excitons emits, dark exciton emits, and we can, in changing the direction on in-plane magnetic field, we can change the plane of polarization of these excitons. And it was observed in experiments. So this is this is experimental results. Here the peak corresponds, it's called luminescence peak, corresponds to emission of bright excitons. This luminescence peak corresponds to gray excitons. And if we apply in-plane magnetic field, we see that, so this is original volume Z magnetic field. In this, if we apply magnetic field, we see that the emission of the dark states becomes huge, and the emission in the maximum at 12 Tesla, it becomes 40 times larger than the emission of bright ones. So this peak becomes extremely large. Moreover, this is not only one peak; it can consist of two ones, which are can be observed here. And again, at zero magnetic field, we can see only gray exciton emission. But if we apply magnetic field, we see the second peak, which corresponds to dark states, which is growing due to this brightening effect. And this growing is quadratic as our theory predicts. So the deviation, difference in this growing for gray and dark exciton, it's because of occupation number. So it depends on the. So if you divided this intensity on this parameter on this parameter, you get just Boltzmann factor. And finally, we can rotate. We can orient magnetic field in plane, and let's define the zero angle in parallel to magnetic field, and start to rotate polarizer. And we will see that if polarizer is polarizer elongated along the magnetic field, we see only the dark exciton emission. But if we rotate it on 90 degrees, we can see the excitation of gray exciton emission. And it's this picture is presented here. So by rotating polarizer and fixing directional magnetic field, we can totally block the emission from dark states and then coming back. And when emission of dark states is zero, the gray states contrary has a maximum of intensity. So this confirms the orthogonality of this polarization of corresponding emissions. And finally, we applied magnetic field, both magnetic fields, perpendicular and parallel. And here we see that for a fixed parallel magnetic field and increasing the perpendicular magnetic field, we can see how we can change the content of or amount of light which dark and gray excitons emits. And so for particular case of magnetic fields, we also check the polarization properties of these materials and also see that the emission of gray and dark excitons are perpendicular. So I'm finished. Thank you very much for your attention.
Okay, so thank you very much for being giving so nice talk. Let's send the speaker, and you are very precise. So we have 5 minutes for the discussion. So please ask your questions.